So what exactly did Professor Lewin do? He's demonstrating that from the same ground point, which is the outer loop, that you get two different voltages. Well, no. Sorry about the shaking. What is going on here? Well, the loop in which the battery consists of is a source. And when he's got the loop in the field of the solenoid, it is also a source. He's doing something rather interesting here. He's probing the differential voltage of each resistor. Now he's using two oscilloscopes so that you can see both pulses individually. But there's also an interesting thing about this with oscilloscopes. Now, if you're an oscilloscope user, you'll know that every channel has a ground. Well, what happens is you have to think about how you're going to probe a circuit with an oscilloscope. There are chances where the ground lead, which is the little clip wire that's hanging down here, this would be the ground lead, can cause what's called a current loop. So effectively, what he's doing is he's showing everyone his pulses on two different scopes, and this solves two unique problems. One, you can display two pulses on two different screens for clarity, but it also eliminates the problem of a current loop. Now, where is the current loop? The current loop, if this were on one oscilloscope, is leaving the positive where it says I, and it's going into the ground lead. The ground goes up the outer sheath of the cable into the oscilloscope. The oscilloscope will measure both positive and negative voltages through the positive tip, but everything to that instrument is relative to chassis ground, which is 0 volts. So what happens here is this induced current will flow up the ground clip, up the cable on the outer sheath to the outside ground of the BNC connector. Then, because each channel of the oscilloscope is connected to every other channel through the ground, mind you, that current will flow back up the other cable, out the ground clip, and it will return back to the negative terminal, thus creating a large ground loop. A lot of times when we perform these ground loops by accident on our oscilloscopes, we will either burn up our oscilloscope cable, or more commonly, we will smoke the little lead clip that comes off of the oscilloscope probe, and I'll show you what that looks like in a moment here. Not the smoking, mind you, but the probe clip. So here's the wimpy little probe clip. Now these aren't supposed to handle a lot of current, they're just supposed to ground the circuit. But a lot of times when we make a mistake, we will short circuit our current through the scope, and we will burn up our probe. And that's a big no-no, but that happens a lot. So his circuit achieves two interesting goals at the same time. Not only is he showing you a flipped 0.1 volt, which is being probed improperly, but he's also having to do so because it eliminates the current loop. Now, to do this correctly on the same oscilloscope, you would have to either choose a different ground location or use a common ground location. Ideally, if you were to pulse the circuit, you would put your clips, both clips or one clip here, probe the 0.9 volt pulse, and then you would take your other probe and you would put it up here. Now, why would you do that? What you're measuring is the total voltage coming out of the system, which is 1 volt, which is KVL, because the source is 1 volt. Therefore, this point here must also be 1 volt to this ground reference. And so what you would see on his scope screens, which would dismantle his argument instantly, is that on one scope, on scope 1, if we move the probe to where it belongs, which is not here, but rather to have the same ground connection on the same scope, which we can do later, and to probe here at the input node of the circuit, which we would get then, of course, because we know what we're doing, a 1 volt pulse. And because we know that we have a current flowing, we know our resistances. We have a current flowing of 100 milliamps. Sorry, I'm not left-handed. We know the voltage drop across this resistor, and we know the total voltage, so we must know the voltage across this resistor. And then if we wanted to, we could go back and we could move the ground and the probe to probing just the 1 ohm resistor by itself and prove that it is also 0.1 volt. And so we could probe everything individually to prove that what Professor Lewin has accused KVL of breaking down is a complete falsehood. Now, if you wanted to, you could also buy what's called a differential probe, which is what you should be using in this kind of a circuit situation. Or you could invert and subtract, depending on how your scope works, or invert and add rather. But a differential probe will allow you to float the probe measurement on a resistor or on an active circuit while you're grounding another part of the circuit, and so you don't perform ground loops as we have already explained. But of course, Professor Lewin doesn't have a differential probe at his disposal. He would rather make up physics as he prescribes. So we will go back and we will demonstrate this as a correction when we have a circuit set up. I do not have a circuit set up at the moment. You can do this yourself. You can get a battery and a couple of resistors and play with your meters and see what you get. Your meters will lie to you if you let them. So it's up to you to know what you're doing.